All right, section 4.3, we're taking a look at arithmetic in the Hindu-Arabic system. And that sounds super scary, but did you know Hindu-Arabic is the system that you use? All right, that's the name of it. So every now and then you'll see somebody on some social media site start talking about how nonsense it is that in schools these days they're teaching this because they don't know what they're talking about, right? Like this is our system and this is its name. So what I want to first introduce to you is something that you know, but you may not know it by this name, and it's called expanded form. Expanded form is a form in which the value of each digit in each position is made clear. So it's a way that we would write, for example, this number, 942, more clearly as to what it means. And so this is written first in words. We're thinking of it as 900, 4 tens, 2 ones. You can think of it in terms of bills, if you'd like, because hundreds, tens, and ones are certainly dollar bills we have. That works nicely. But there's another way to write it too, instead of words, that is sometimes helpful, and this is where we're headed with this, is to write down that 900s means we have 9 times 100. And 4 tens means we have 4 times 10, and 2 ones means we have 2 times 1. And each of these numbers that are in the parentheses are powers of 10, because we have a base 10 number system. And I believe in the video we probably talked about why we have a base 10 number system. Nod your head yes if I did. Did I do that in the videos? Or is it no? Okay. The reason we have a base 10 number system is because you have 10 fingers, right? That's why. You'll remember in the video I talked about if we were Fred Flintstone. Do you remember what base system we would be using? It's 8. So cartoon characters tend to have 3 fingers and a thumb, right? So they have a base 8 if they were working with their digits, right? Their finger digits, right? So these are base 10 numbers. What that means is that we can rewrite each of them as a power of 10. So instead of writing 100 as 100, I can write it as 10 squared because 10 squared is 100. I can write the number 10 as 10 to the 1, even if it feels weird that I do so, I can. And does anybody know how I can rewrite the number 1 as 10 to a power? I can't hear you. What? What was that, Kenan? Well, I need a power. I need a number beside it, right beside the 10. Does anybody know what that power should be? Yeah, it's a 0. It's a power of 0. So 10 to the 0 power is what goes there. And there's actually a quick way of remembering what these are doing for us. So this power 2 is actually telling you that, at least one way to remember it, is that there's 2 zeros in the number 100. Right? The power 1 tells you that there's 1 0 in the number 10. And the power 0 here tells you that there are no zeros in the number 1. Okay, so if you want to remember it that way, that's a quick way to remember it. So what we're going to do is we're going to take some numerals and look at writing them in this expanded form, or taking them in this expanded form and writing it back into standard form. So the first one we have is the number 12,398. So each of these numbers are going to be present in what I'm writing down. I've got the 1. And then what place value is the 1 in? It's in the 10,000s place, so we write down that it's multiplied by 10,000. And the number 2 is in what place? The thousands place. And the number 3 is in the hundreds. The number 9, tens, and the number 8 is in the ones. And if I'm remembering right, what my math lab will have you do is to write this down, and then it's also going to have you write down what it is with powers of 10. So what is 10,000 in terms of 10 to a power? It's 4, because there's 4 zeros. Is that okay? How about the number 1,000? It's a 3. And the number 100? It's a 2, so 10 squared. And the number 10 is 10 to the 1. And what do I do for the number 1? 10 to the 0. And you'll notice that the powers of 10 go downhill, right? 4, 3, 2, 1, 0. That happens every time. The one caveat to that is that if there is a 0 in one of those places, we still write it, right? So if it had actually been 10,398 instead of 12,000, I'd still write the 0 where I wrote the 2 and multiply it by 1,000. Now, you see that actually happening in the next digits, or the next problem that we're doing. So I have this written in sort of the reverse order. It starts out in those powered forms, and it wants us to simplify it and to write it back into a number that's like 12,398. Okay? Now, if you're careful and you notice, you can see if they're all there. This is 10 to the 5th, 4th, 3rd, 2nd, 1st, and 0. Are they all there? They are. And because they're all there, that makes it really nice because all these numbers at the front are the only numbers now that I need to write to rewrite this in simplified form. There's a 5, a 0, a 3, a 5, a 6, and an 8. This is the number 503,568. And we just read it straight off of there. If you're concerned, you obviously could put that expression in your calculator, right? Make sure that you didn't miss something, right? And it would spit back out at you as well, 503,568. Okay, so far so good. Okay, none of that's new. Maybe you haven't thought about the powers thing before, but none of that's actually really like brain new information. Like it's just not brand new. So why are we doing that? Well, we're going to move into using it here in just a moment as a reminder more than anything. But there's one more piece of information that I need to remind you about that seems a little bit disconnected to what we're doing, but there is a connection. And this is a property that you've learned probably somewhere in about 4th or 5th grade is where you first see this listed. It's called the distributive property. And the distributive property is often presented sort of in reverse order of the way that I've written it. You typically see this piece written on the left-hand side and the other piece on the right-hand side. And somebody probably drew some sort of arrows through or something like that, these arches through that told you that the A is multiplied by the B and the C. Nod your head if that looks familiar. It should look familiar, okay, the distributive property. You use it a lot in algebra when you're like foiling or distributing out polynomial expressions and things like that, right? This is a property that we use. Again, it feels a little disconnected, but there is a connection that we're going to see very quickly in our next example. So what we're taking a look at is we're taking a look at the way that expanded form actually helps us to do arithmetic. And we don't even think about it happening, we just do it automatically. So let me show you what that looks like. All right, so we've got some simple arithmetic values, right? There's nothing about these that's anything difficult. Your calculator could do them. You could do them easily by hand. The numbers are not big, right? But I want to show you why it is that expanded form actually supports the process that you know how to do. So we're going to, it says add or subtract in expanded form. So I'm going to show this to you in why it connects the expanded form and the distributive property. And then I'm going to show you how we can write it up in a more concise way, okay? So let me show you the why and how it connects first. The 75 is 7 times 10 to the first and 5 times 10 to the 0. Whoops. All right, that's what we looked at on a couple slides back. And 34 is 3 times 10 to the first and 4 times 10 to the 0. Okay, so we just wrote it in expanded form first. But what the distributive property says we can do is that we can group together the pieces that are actually being multiplied by the same power of 10. So the two that I've highlighted are both being multiplied by 10 to the first, right? So I can sort of like move them together, regroup some things, and I can shift this around to say that I'm going to add the 7 and the 3 first, and then I'm going to multiply by the 10 to the 1 second. And I can do the same thing with the 5 and the 4. I can add the 5 and the 4 first, and then multiply by the 10 to the 0 second. That's the distributive property. That's where it's coming into play. Now, in a very real sense, if you think about bills of money, this is exactly what you would do. If you had $75 and then somebody gave you $34, you would put all the tens together, at least most of you would, and you'd put all the ones together, right? You'd regroup them, right? Some people don't do that in their wallets. I don't know how you find your money if that's you, but most people do. All right, so we would regroup them and we would do the addition of the tens all together. So our tens, there's actually 10 tens. So I'm going to just write the 10 here for the moment. And then there are 9 ones, or 9 times 10 to the first, right? Oops, I'll just do it like this for consistency. What happens when we have 10 tens? What is that? What's 10 tens? It's 100, right? So 10 times 10 is actually 10 squared, right? That's what it is when we multiply 10 times 10. So this is 1 times 10 squared. I've turned my 10 tens into like a $100 bill in essence, right? Maybe you wouldn't do that, but pretend for a moment you did, right? And then I didn't have any tens left over, so there's 0 tens left over, 0 times 10 to the first. And then there's 9 times 10 to the 0. And this all ends up giving me the number 109. So that's where all these are sort of piecing together between the expanded form and the distributive property. But what it actually looks like when we do it, both inside of my math lab and when we do this in sort of the standard form, but we're going to show it with expanded, is that we tend to write it from the top down. And so it would look like this. 7 times 10 to the first plus, what's my number? 5. 5 times 10 to the 0. And then we have 3 times 10 to the first. So we're grouping them in columns, right? That's the grouping that you see happening here. And then you have your 4 times 10 to the 0. And then we add sort of vertically down, right? So there's 9 times 10 to the 0 here. We have 10 times 10, times 10 to the first here. Of course, that breaks apart into being 1 times 10 squared. The 0 times 10 to the 1, and the 9 times 10 to the 0, just like we saw in that other version of it for the number 109. So this is how my math lab is going to have you put it in, if I'm remembering correctly, on this site, okay? Okay, so there's addition. So let's take a look at what happens with subtraction. And we will just do the vertical method now because that's the one that's the most conducive for what our version is going to look like inside of my math lab. So we're going to write again, this is 7 times 10 to the first plus 4 times 10 to the 0. Okay. And then I have 48. Well, this is 4 times 10 to the first and it's 8 times 10 to the 0. But there's a subtraction sign here, right? So I'm subtracting off everything in the number 48. I'm subtracting the 4 tens and I'm subtracting the 8 ones. And do you see that we're going to run into a problem? What problem do we run into?
4 minus 8.
Yeah. 4 minus 8 is sort of backwards, right? I can't have 4 ones and actually give somebody 8 of them. I don't have 8 to give them. So this happens all the time when I exchange money with my kids, right? Is that I've got to give them change back essentially for something, right? So what we do is that we rewrite this in a slightly different way, right? So what we would do in our standard algorithm is we do something called borrowing. That's what we've typically call it. More contemporarily, people like to call it regrouping, which is fine too. It's the same thing. But we take one of these tens and we actually turn it into 10 ones, right? So this is going to leave me with 6 tens. And if I have 10 ones plus the 4 ones, I get 14 ones. So I actually have 16 times 10 to the first, not 16, sorry, 6 is what I meant to say. 6 times 10 to the first. I have 14 times 10 to the 0. And then I really can take 4 away from the 6, and I really can take 8 away from the 14. So 6 minus 4 is 2. So there's 2, 10, that should say 10 to the first. 10 to the first. And then 14 minus 8 is 6 times 10 to the 0, which is the number 26. Okay. So the expanded form really does give sort of visual evidence to what we're doing, right? We're really taking 110 away, right? One of the $10 bills or whatever away and turning it into 10 corresponding ones. All right, there's another thing there's 2 more things in this section. The next one we're going to take a look at is a very old school device. It's called an abacus. Have you heard of an abacus before? Okay, good. So we're going to take a look at one version of an abacus. It's a very common abacus version, but not the one that everybody's always seen. So an abacus is one of the oldest methods for speed calculating, okay? There's a bunch of beads on rods, okay? So this is a picture of one down here at the bottom. You'll notice some of the beads are blue and some of them are black. on a physical abacus, they're not colored differently. This is their effort to sort of draw attention to the fact that some of them are moved toward the middle, and they've colored those in black, and some of them are moved sort of away from the middle, and those are colored in blue. Okay, but they're really all the same color on the physical object. This is a physical object. What you don't have the ability to do is to break the object apart and take the beads off. Okay, we're not in shop class. We're not doing that. We're not Destructo Child either. I've got some of those in my house. We're not doing that, okay? So this is an object. The beads have to be on there somewhere. They either have to be pushed toward the middle or pushed away. The beads that are the beads that are pushed toward the middle, let's start with that one, are called active beads. They contribute toward the value that we're calculating or we're expressing. And so those are the ones that are in black. The ones that are pushed away are inactive. They're just on the rod because we're not destroying the object and taking them away. But they're still there because they're on the object, but they're not being used for calculation, okay? The ones that are above the middle rod are worth 5. So if it's pushed away, it doesn't count. If they're pushed down to the middle, it counts and it's worth 5. The beads that are below the rod are worth 1. So again, pushed toward the middle, they're worth 1. Pushed away, they're not worth anything. So we're just going to, one more thing, place values. The biggest place values on the left, smallest place values on the right, just like we would write our numbers normally, okay? So what we're going to do is we're going to write the numbers represented on each rod, and therefore the number that's actually represented by this object. So let's just start. It doesn't matter if we start on the left or right, so we're just going to read from left to right. So on the leftmost rod, you notice there are 3 beads that are pushed toward the middle, and beads below the rod are worth 1. So this would be the number, what? 3. This is the number 3. I'm just going to write it underneath here. Right here, the second rod, I only have 1 bead from below pushed toward the middle, which means this is the value 1. The third rod is the most interesting thus far because there's beads from above and below pushed. So the one above that's pushed toward the middle is worth how many? 5. Yeah, it's worth 5. And then the ones below are each worth 1. So I have 5 above and 2 below, which means that this rod would have the value 7. On the fourth rod, there's nothing pushed toward the middle. So what value is represented here? It's 0. And on my last rod, I have 1 pushed above, 1 pushed below. It's 6. So this number is 31,706. Okay, that's how we read an abacus. Okay, so the next one you're going to take a look at is going to have a picture, and I want you to write down what you believe the number is. Okay, here's our picture. Write down what you believe the number is, and then everybody's close-ish enough to somebody that I want you to grab somebody nearby and say, did I get what you get? Let's just check, all right? Check and see that you got the same thing, and then we're going to touch base all together and make sure that everybody has the same thing. Some of you who are in these single desks are not talking to anybody. So as soon as you get them written down, like turn behind to somebody or in front to somebody and see if you can check with somebody nearby. Check with somebody nearby. You can do it. Just check to make sure they're the same. All right. Okay. Do we have a number? What number do we have? Some of you are saying yes and some are saying no. What number do we have? 10,256. Okay, so let's just check and make sure. The first one's a 1 because there's 1 pushed from below. The second one's a 0 because there are no beads pushed toward the middle at all. The third one's a 2 because there are 2 beads pushed from below. The fourth one is a 5 because it's 1 bead from above. And then the last one is a 6 because it's 1 bead above worth 5, 1 bead below worth 1, so we've got a 6. Okay, now we're going to turn the direction around. Obviously in my math lab, well, I wish they did. We should request that they have these like sliding things that allow you to actually like make the image, but I don't think they do, at least not yet. So what we're going to see is we're going to probably see something in multiple choice form, but we're going to practice actually drawing an abacus out. So draw yourself a big old giant rectangle, or at least in the space you have. And it needs 5 rods on it, just like the ones we've been working with. And it needs a middle rod. Doesn't have to be exactly in the middle, but somewhere in between. And every rod needs to have 1 bead above the middle rod and 4 beads below. They are either pushed to the middle or they're pushed away, but they all have to have 4 beads on their rods. Below, 1 bead above, okay? So the first number says 70. How do I get a 7? Okay, we get a 5, that's 1 pushed right here, and 2 below. My beads are not going to be symmetric, but you can use your imagination. But they're supposed to be 1 bead above. We have 4 beads below. I only have 2 beads below, so what do I need to do to get 2 more beads? Yeah, I need to draw them and put them on the bottom, right? I need to push them down. So these are my 2 missing beads below to make up the 4 beads that are below the rod. Notice my colors are all going to match because the rod really would have the same colors. I'm not going to distinguish the blues and the blacks like they did originally. The second number is 0. What do I do to get a 0? Yeah, they're all pushed down or pushed way up, right? So I push the bead on top to the very top, and I push the 4 beads on bottom to the bottom. 1, how do we get the 1? Just 1 below. So 1 on bottom looks like that. The 1 bead above the rod needs to be pushed away, and the other 3 beads on the bottom need to be pushed away as well. 6. What do I do to get a 6? 5 and 1. So the 5 on top, the 1 below. I need 3 more beads on the bottom, pushed away. And then the last number is a 3. How do I get a 3? 3 on bottom, pushed toward the middle, like this. The 1 on top would be pushed away, and I need 1 more on bottom pushed away. Every rod has 5 beads, 1 above the middle, 4 below. There's always going to be a bead above the middle, and there's always going to be 4 beads below the middle. This is a physical object. They slide up and down is what they really do. Like you would put them flat if you were looking at this, and you'd slide them up and down. Yeah. Okay, any questions on our abacus? Last feature in this section, we're going to take a look at something called lattice multiplication. So if you've been in number theory, our elementary ed number theory class, you've seen this before. But this is actually taught in elementary schools' curriculums, depending on the curriculum that your school used. So you may have seen it way back when as well. This is actually the method that resonated the most with my mathematically minded daughter, who normally would have used all the standard algorithms that everybody normally gave, and they didn't make sense to her. So the lattice multiplication does this. You create rows and columns for your digits. You divide each box diagonally. And then you compute each product along its row and its column. The tens digit goes in the top left. The ones digit goes in the bottom right. And then we add along the diagonal from right to left. So jot those down. And then we're going to do one example on this slide and then one example on the next. Okay, so I've got a 2-digit number and a 3-digit number, 23 and 187, right? So I need to draw a box that's either a 2x3 or a 3x2 box, and it doesn't matter which. my space lends itself better to making my box long, or wide rather, instead of long. So I'm going to draw mine as 2 long like this and 3 wide when you sort of break it into a grid. Okay? But if you wanted to do it with 2 wide and 3 long, you could do it that way too. The number 23 has to go along the right-hand side if you've made it like this, and then the 187 along the top. And then you split each box diagonally like this. Okay, everybody good so far? All right, so what it describes is that you're going to do all the multiplication first and all the addition second. And that is the primary way that it differs from the standard algorithm where you multiply and you carry and you add something in the middle of your multiplying, right? That's the algorithm probably that you used most frequently. And that's the algorithm that trips people up sometimes because you're adding and you're multiplying within the same step. So this one isolates the operations, which is kind of nice. So what we're going to do is we're going to multiply the column number by the row number. So if I'm on column 1 and I have this row that's number 2, I'm just going to multiply 1 times 2. And 1 times 2 is 2. And I write that single digit number down here in the bottom right-hand corner of that very first box. The next one's a little bit more interesting where you can see why we've got the boxes the way we do. 8 is the column, 2 is the row, so 8 times 2 is 16. So with the number 16, I write the tens digit in the top left, the 6 for the ones digit in the bottom right. That's 16. Okay? 7 times 2 would be 14, and it goes in this box right here. Okay? And if you're a little rusty on some of your multiplication facts as they get bigger or whatever, can you use your calculator to do this? Sure, you can. Just check yourself or whatever. It's fine. All right, next one. We have column with the number 1, row with the number 3. So 1 times 3 is 3. Next one, column with the 8, row with the 3. 8 times 3, 24. Last one, 7 times 3 is 21. Okay, so that's all the multiplication you're going to do. You're not going to do any more multiplication. Next step, you're going to extend the diagonals like this out. And we're going to add along the diagonals. So you have to start in the bottom right corner. Everything we add has to be in the box. No adding the 23 or the 187 from the outside of the box, okay? Only adding numbers that are in the grid. So this bottom corner, not very exciting, it's just the number 1. It just gets written down. But in this one, it's a little bit better. So I have 4 and 2 and 4. What's 4 and 2 and 4? It's 10, right? When we get to the 2. Yeah, we get to 10. So we write down the 0 and we'll carry the 1. And I've changed colors because I wanted you to make sure you see what I do with the numbers. So this is the number 10. The 1 gets carried to the next diagonal. The 0 gets written down. A lot like you do with the standard algorithm for addition, which is our normal addition algorithm. Now we're going to add this next diagonal together. So I have 1 plus 1 plus 6 plus 2 plus 3. What'd you get? 13. That's what I have 2 in my head. 13 good? So we're going to write down our 3 and we're going to carry our 1. Last column, or last diagonal, excuse me, I have a 2 and a 1 and a 1, which gives me 4. And our answer then is right here, 4,301. And how could you check that? Don't ever think this. Yeah, with a calculator, right? You should make sure you get the numbers right. There's nothing in this that's really like earth-shattering in terms of, did I do it right? You should know if you did it right. Just check it and see. If it's 4,301, you're good to go. Okay, let's try one that's a little bit bigger. 912 and 483. How big will my box be? Yeah, close. 3 by 3. So it's going to be a 3 by 3 box, which means there's going to be 3 rows, 3 columns for a total of, how many boxes? 9. 9 boxes here. And they're not evenly distributed on mine. My picture's a little bit lopsided, but that's okay. It doesn't matter with the 912 and the 483 because they're both 3 digits where you put them, except that they go on the top and on the right. But you could flip these around if you wish. I'm just going to do them in order like this. So 912 on the top, 483 on the side. And we will make all of these boxes split along diagonals. Something like that. Okay, so we're going to do all these multiplications. There's 9 multiplications to do. 9 times 4 is 36. So 3 in the top, 6 in the bottom. 1 times 4, 4. 2 times 4, 8. 9 times 8, 72. Good job. 1 times 8, 2 times 8. Perfect. 9 times 3, 1 times 3, 2 times 3. Cool. Okay, I know that was really fast, but is everybody okay with it? Okay, simple multiplication stuff. That's back to 2nd and 3rd grade. Y'all got this. No problems. Standard diagonals, right? Okay. Whoa, that was funny. Here we go. All right, bottom right corner, inside the box only, there's a 6. Next diagonal is 6 plus 3, which is 9. Next diagonal have 8 plus 1 plus 8 plus 7. Somebody said it, 24. Very good. 24. 4 here, 2 carried. 2 plus 4 plus 2 plus 2? 10. Good. I'm just throwing numbers at you today. We're just going to keep throwing numbers. Okay, so I have 1 plus 6 plus 7? 14. Good. And carry my 1. 3 plus 1 is 4. And looky, there's your number just right there. This is 440,496. Somebody grab a calculator. Check to make sure we're right before we move on. Nobody wants to check. Are you worried? You're going to want the calculator out for the next lesson anyway, so go ahead and grab it if you don't have it. Did it work? Did anybody check it? Yeah. Okay, I've got a couple people saying yes. All right, cool. So this one's correct.